In this recording, we're going to do an introduction to limits. So we'll consider two types of limits in this lesson. Your limits that approach infinity, and then limits that approach specific values. Okay? So the first type will be those that approach infinity. And you can kind of think of these like your end behavior of a function. So when we say, what's the limit as x approaches infinity of x cubed? You kind of think of, okay, if I substitute in a really large number and cube it, what's that going to end up being as x gets really, really big? And hopefully you think, okay, that's just going to be an infinity, right? And then if I were to sub in a really, really large negative number that approaches negative infinity, and then I cube it, what would that look like? Well, a negative cubed is always going to come out negative, right? So the bigger the negative, bigger its absolute value, closer it is to negative infinity. Let's think about what that looks like graphically. So if I think about the graph of y equals x cubed, basically have a graph that kind of looks like this, goes to the origin, doesn't have any vertical asymptotes, but it has that type of shape. As x gets closer and closer to infinity, y gets close to infinity. As x gets closer and closer to negative infinity, y approaches negative infinity. So it is the end behavior of that function. Let's consider another function that's going to require us to do a little algebra. With this one, we can't just simply sub in the infinity for x, because what would we get? We'd get like an infinity in the numerator and an infinity in the denominator. So what we're going to do is look at the largest power of x. So in this case, it's x squared. And we're going to divide all the terms by x squared. Okay, so we're going to divide by x squared. As long as I'm dividing all the terms, I'm maintaining the equality of the expression. Okay, so as you rewrite it, this is really important. Rewrite the limit as x approaches infinity. We haven't taken the limit yet, so we need to continue to write it. Now let's rewrite what's left. That just simplifies to be a 1. This, the x's divide out, so I have 7 over x. Bottom left is a 3. Bottom right, negative 2 over x squared. All right, so let's consider what happens here. The limit as x approaches infinity of 1, well, it's just a 1. So that's still going to just be 1, right? Doesn't depend on what x is. The limit as x approaches infinity of 7 over x. Well, consider it's hard to consider infinity. Think about the biggest number you can think of, like 1,000,000 or something. You divide 7 by 1,000,000, divide 7 by 1,000,000,000. It's getting really, really close to 0. Let's basically say that's a 0 right there. Okay? As x gets close to infinity, that gets close to 0. In your denominator, we're going to speak shortly, about when we have constants. What's the effect of x approaching any number? That number 3 doesn't change. It doesn't depend on x. And then finally, same situation as with the 7 over x. When you sub in infinity into 2 over x squared, the denominator gets really big, the numerator stays constant. That basically approaches 0. So it works out to be just 1 over 3. And we can examine that with our calculator. Let's check that out. Let's go to our calculator. Let's enter this function. Okay, let's look at the graph of this function. We'll do a zoom 6. Okay, so the graph seems to level out with a horizontal asymptote. Kind of hard to tell what its value is. Let's look at the table. Okay. As we get closer and closer towards infinity, let's kind of scroll down in our table here. Well, it's hard to tell what this number is going to be because it's varying so much. Once we start to get into decimals, we'll be able to see it. So let's get a second table set and let's change it to be like 1,000. Yep, it's getting really close to 0.3333, which is what we thought it would get close to as x gets very large. We can even make it bigger, make a greater point, make it 1,000,000. Yep, when you get towards 1,000,000, the y values are getting very close to 1/3. Point made. Okay, so those are our limits as x approaches infinity. Now as x approaches a particular value. So check out this graphic here. And you don't need to write this down necessarily, but let's appreciate it. We have our left and right hand limits. We've talked about as x approaches a from the left and as x approaches a from the right when we talked about intermediate behavior around vertical asymptotes. Well, this red portion of the graph is what's happening as x approaches this particular value a from the left, and the blue is as x approaches a from the right. And they're both approaching that same value, that same y value, which we're going to call L. So that's the limit. They get closer and closer to that y value. Okay? So that's our left-hand limit, and that's our right-hand limit. I think there's a little typo. Let's make this a right. And then finally, the double-sided limit. So if the limit exists, the limit from the left and the limit from the right both approach the same value, L. This is kind of another case that's a little bit unusual, where both the left-hand limit, which would be over here, and the right-hand limit are both the same value. So as x gets closer and closer to 2, the y values get closer and closer to 4. But when you actually get to 2, the actual y value for x equals 2 is a 6. That's okay. We can still have a limit here of 4, but it just means the graph is not continuous. You'll learn more about that in calculus, but I did want you just to see that specific case. Okay, so let's talk about some simple examples where, and I would like you to write down, let me copy this in so we have it, limits that approach specific values. And we'll start with some simple ones and work to some more complex ones. So this first one, limit as x approaches 5 of 7. Well, the function is just 7. The function doesn't care what x is, right? So the function is just going to be 7 no matter what x is. So the limit of any constant is that value. Does not have any dependence on x. Example 2, does depend on what x is. So x isn't approaching infinity here, it's approaching a specific value. So you get that value by just substituting in. So you just make that substitution of 2 to the 5th. Increasing the complexity just a little bit, we've got a parabola here, a quadratic. Well, we're still just saying what's happening to the y value as x gets close to 2. Okay, so let's just substitute in a 2 and evaluate that. We got a 4 plus a 6 minus a 5. Looks like 5, right? And again, what we could do is look at the graph of this parabola and see that as x gets close to 2, the y value is getting closer and closer to 5. This next example is a tiny bit more complex, but we can handle it. Okay, we're going to see this value that x is approaching. So we've got a rational function. And as long as this value of 4 is not going to make it undefined, we don't have any problem. So let's go ahead and make our substitutions. Okay, so just do the math in the numerator. Looks like 21. Do the math in the denominator. 16 minus 8 looks like an 8. I can't simplify that. So there it is. If I wanted to check this, I could do what I did before, go to my graphing calculator and enter this and see what's happening to the function around x equals 4. Let's do that now. So we'll enter that function. Let's quit out for a second and just see what 21 divided by 8 looks like. Okay, so we're looking for the decimal 2.65. Now when I go and check out my table, let's set our table up at 0 and go by ones. Okay. We can see there's a couple of errors, but we're really interested in when x approaches 4. So we get down here to 4. And in fact, when x is 4, y is 21 over 8. And we're going to continue to use the calculator to confirm our algebra. All right, so let's get into a couple of kind of tricky examples here. Go ahead and do what we did before. Go ahead and jot this one down. And let's make our substitutions. So when we substitute 3 into the numerator, that doesn't look like a problem. However, we do see a problem down in the denominator. Okay, so we've got a 9 plus a 6, that's a 15 minus 8, looks like 7 over 0. Well, that's undefined. And so the limit here does not exist, because what you're doing is approaching 3 in a rational function that has a vertical asymptote at 3. So the limit does not exist. This is undefined. And what we would say here is, the way we would answer it is the limit does not exist. If you wanted to take the time to graph this on your graphing calculator, you would see a vertical asymptote, and you would see that the intermediate behavior, the behavior to the left and the right of 3, is not consistent. They're both approaching different directions on there. So let's check out this next one. So this next one, when we sub in a 2, so my numerator, I've got 4 plus a 2, that's 6 minus 6, so that's 0. My denominator, 2 minus 2, that's a 0. We have a special mathy name for this. We call this indeterminate. Okay, again, indeterminate means there is a limit, but we can't tell what it is from this 0 over 0. Okay, so usually means there's a hole in the graph there. The right-hand limit and the left-hand limit are the same, kind of like we saw here. Right-hand limit and left-hand limit are the same, but right at the point 2, 4, it may not have another point up here. It may just be undefined, maybe indeterminate. So there's a hole there. Okay? I misspoke. It's not undefined. It's indeterminate when it's 0 over 0. Undefined is if the denominator is 0 and the numerator is a constant. So here's a technique we can use. Let's factor the numerator. So we're going to keep writing limit until we've evaluated the limit. Factor that numerator. And typically it will be a shared factor with the denominator. So what I can do is divide out the common factor, and now I can just evaluate the limit as x approaches, I don't know why I put infinity on that previous one. It's supposed to have been a 2. As x approaches the x plus 3 expression. So as x approaches 2, when for x plus 3, that's just simply 5, right? 2 plus 3, 5. So there's our limit. we can check this by grabbing our graphing calculator and seeing if in fact on either side of that function we have a value that gets pretty close to 5. This will be a pretty powerful technique. Okay, so let's set up our table. We'll do second table set, and we may as well start it to be near 2, right? Because that's the point that we're going to find the limit of as x approaches 2. And we'll do second table. So we can see there's an error at 2, so we can't tell what the limit is from there. We can get kind of a good idea because check out the rest of it. It goes 3, 4, blank, 6, 7, 8, 9, right? It's probably a 5. But here's something pretty cool. Put your cursor right on 2. Then with our new operating system, you can just hit the plus key. And that's going to allow you a quick shortcut to change what the table is going by, the delta table. So let's go 0.01. We'll go by 100th. Hit enter. And now pretty well I can see that on the left side, okay, my left-hand limit is 5, right? It's going really close to 5. My right-hand limit is getting smaller and smaller, approaching 5, so that it makes sense, what I figured out from algebra, that the limit is 5. Okay. So one final example I'd like to look at that's a bit complicated. We've got square root in the numerator here. Let's go ahead and use our approach of substitution. Okay, so up in the numerator I've got square root of 9, which is 3. 3 minus 3 is 0. Denominator 0. This is indeterminate again. But it does mean there is a limit. I can find it algebraically. The work is a little complicated. But I can also find it graphically. So let's enter this function in our y equals. Okay, let's take that approach one more time. We'll go second table set. Let's get near 7. We'll keep our table going by 1s to start and then just see what happens. Again, the reason I'm starting it at 7 is that's the value that x is approaching in my limit. So I'll go second table, check it out. So we know there's an error at 7, but what's it approaching? Well, it's kind of a little hard to tell. Looks like around 0.16, but let's get right on 7, change the delta table, what we're incrementing by hitting the plus key. I'll do a shortcut down here, and you can just make it 1/100th. Now when we hit enter, we can see that the left and right of 7 is getting really close to 0.1666, which would be 0.16 repeating. Okay, so graphically, or numerically, we have found the limit to be 0.16 repeating. If you're interested, I'll proceed and show the algebraic work to get this. But if you're okay with just knowing that we can find this type of answer numerically, then you're all set. Thanks for watching. Okay, so if you wanted to continue with me, here's what we're going to do. I'm going to show you how to do this limit as x approaches 7. What we're going to have to do is this technique called rationalizing the numerator. Okay, little calculus technique here. So again, we showed this is indeterminate. We can't really proceed. We can't factor out the numerator. I'm sorry, we can't factor the numerator like we did here to divide out a common factor. So what we're going to do is rationalize the numerator by multiplying by the conjugate. Okay, if you recall, the conjugate is the same exact thing, but a plus 3. Right? It kind of creates a difference of 2 squares because the numerator has a binomial that is the same as this with the opposite sign. I'm going to hold off on distributing the denominator. Let's just kind of see what happens up in the numerator. So in the numerator, multiply and multiply. But the thing is, can you see how we're going to have opposites? When I multiply the negative 3 times this and the positive 3 times this, they're going to be opposites and add to 0. So I'm not even going to show that. I'm just going to show what happens when I do square root of x plus 2 times itself. That should just be x plus 2, right? And then when I do negative 3 times positive 3, I get a negative 9. My denominator is going to be x minus 7, in parentheses, times this expression. Okay. Now, my numerator really could just be written as an x minus 7, would you agree? Which shares a factor with the denominator. So that divides to 1. And so what I'm left with is, I should be writing limit, and I have been sloppy here. Limit as x approaches 7. We haven't taken the limit yet. So it's still, the limit as x approaches 7 of this kind of complicated looking expression. And you might be saying, what's the point? But we're about to find out. Keep in mind our answer is 1.16 repeating. All right, now I can make a substitution with 7 because I'm not going to cause my denominator to equal 0. Numerator is 1. Denominator, square root of 7 plus 2 plus 3. Well, we know what that's going to come out to be. Square root of 9 plus 3 is 3 plus 3. So I've got 1 over 6, which, when you work that out, is 0.16 repeating. Thanks for sticking with me on that.